Hi, welcome to our next session here in our chapter on feature selection. I already started out by motivating why feature selection is useful as a means to reduce the risk of overfitting, to improve the generalization ability of a model, to filter out, redundant and useless features, and also maybe to reduce the costs of a predictive model during prediction time, or to enhance interpretability. And here in this session, I'm not going to introduce any first algorithms for feature selection, and we're not going to add any more theory to this. So I'll just take a look at, just take a further look at motivating the practical importance of feature selection, and look at a bunch of examples which hopefully help us to sharpen our intuition a bit. And then again, I'll discuss a bit more different categories of selection techniques and so on. But I will mainly concentrate here on some simple examples to see where feature selection helps, or maybe integrated feature selection fails, and so on. Okay, so first motivating example is a bit more on regularization, I guess, than feature selection, but like I said, it's pretty tightly connected. So we'll look here a bit more at this P much larger than N case, and how overfitting becomes increasingly problematic when we increase the amount of included features in our data set, and how stronger regularization becomes more and more beneficial or even required. So what we'll do here is we'll create 3 different data sets through simulation. So I'll use a pretty low number of observations, so 100, but that's not totally unrealistic in medical settings where we, might study some rare form of a disease, or we just have access to just a pretty restricted amount of patients. And we'll now use 3 different numbers of features, so 20 features, 100, and 1,000. We'll draw features from a standard Gaussian. Features will be correlated. The target is simulated basically through a linear function. There's some noise on this. I'm restricting the signal to noise ratio here. All of these details are not too important to understand what goes on. And I will now fit 3 different ridge regression models to the data with a super low setting for the regularization constant lambda, a higher setting, and a very, very, very strong and high setting. And then we'll analyze the results, which we'll do exactly now. So what you can see here is how we vary lambda. Okay, well, I guess we can see it here. So just explained. This here is for the 20 features, this here is for the 100 features, and this here is for the 1,000 features. And on the y-axis, we have relative test error. So relative test error is nothing really complicated. So this is just a rescaled version of our normal squared error on the test set. And we just divide that by the base error, because for the simulated setting, we know that. I guess we know that because we know what type of error we are adding on this linear model here, which is in a certain sense our perfect prediction function. And so what I see on the y-axis now is if we have like a relative test or error of 1, that would mean we are as good as the base optimal model, and we cannot go below that irreducible error. If it's a 2, then we are twice as bad, and if it's 3, we are 3 times as bad, right? So this is kind of through the rescaling, this makes it a bit more interpretable. And what we can now see is that for the setting, the very low dimensional setting, what's the best regularization constant? Well, it's this super low setting for lambda, which is also completely non-surprising, right? Because if our data set is very low dimensional, we don't really need to bias things through regularization. Just like using the linear model in itself might already be optimal, and further biasing through regularization might actually hurt us. Here, we need a medium strength regularization, and if we are in this quite high dimensional setting, we need very, very strong regularization. And all of that is completely unsurprising. Kind of already explained that, I hope. And we are also looking at this further in depth in the dedicated chapter on regularization. So I keep it at that here. So summary, high-dimensional settings require more complexity control through regularization or feature selection. Yeah, let's keep it at that. Second example, maybe a little bit more directly relevant to us here. So this now compares different methods for feature selection, also some methods without feature selection and some regularization techniques on a microarray data set. Again, you can see it has this NP much larger than P much larger than N property. Yeah, and we have a very, very small training data set. So we have a test data set here, which is also not super large, but I guess we also, no, we don't really repeat that here. We just train on the training set and we test on this 54 element dedicated test set. So you should also be a little bit careful here. So this test error will have a very, very high variance associated with it. So maybe we shouldn't trust this too much. And we also take a look at the cross-validated error on the training data set and then the test error here at this dedicated test set. You can see how large scale P is. So this is about 16K features for these very few observations. And it's a categorical encoding with actually 14 classes. So that's also not pretty great with so few observations. And the task here is to identify a certain subtype of cancer. So that's a very, very common predictive task based on this form of microarray data. And this setup and the results are taken from the Hesse-Tipschirani-Friedman book, Elements of Statistical Learning. So let's see what we can see from the result table. So first of all, what methods are we actually comparing? Okay, so we have something like nearest trunking centroids. So that's basically without any extra regularization or a specific form of feature selection. We have like an L2 penalized discriminant analysis. So LDA with an L2 penalty, with a rich penalty, with a support vector classifier that I guess you hopefully already know uses also an L2 penalty. We have a linear model with lasso and then some 1 versus all on top of that apparently to handle the 14 classes. K nearest neighbors, apparently also without regularization or feature selection. L2 penalized multinomial regression, L1 penalized multinomial regression, so that really does feature selection, and the elastic net for the multinomial model. And in terms of columns here, we have the cross-validated error and we have the test error. So I don't want to go into too much detail about differences between the two. So what you can see here is, actually I don't want to discuss that too much. I guess if you compare the two columns and then if you like rank the methods either in the CV error or in the test error column, you'll see that the ranking is pretty similar. So I'll just focus on one of the two, I guess. I don't know, maybe we'll focus on the test error. And we will also compare that with the number of genes used in our model. So what you can see here is that for some of the methods, like, I don't know, maybe let's start with K neighbors. That's so easy and that really doesn't do any, so simple, that doesn't do any form of feature selection. You can see here that uses all features, right? Because it doesn't really do any form of feature selection. Then you have these L2 regularized techniques, like here the L2 penalized multinomial, or let's maybe do the L2 penalized LDA, and they also use all of these 16K features. Why? Well, they regularize, but as we have learned in the chapter on regularization, if we use the L2 penalty, it's very, very, very unlikely that feature coefficients get driven down to exactly 0. It's a bit different for the L1 penalized models. You can see that the model, if we also perform tuning of the lambda control parameter, ends up kind of an optimal setting where only about 270 features are included. Probably something similar happens here with the elastic net that has an L2 component but also an L1 component. Here we have the lasso regression that apparently picks out a few more features, and I'm not exactly sure what happens with the nearest shrunken centroids. Maybe that's not too important for us here. And what you can see now, if you now look at the test error, first of all, I guess we can conclude that if we use a method which doesn't do any feature selection or doesn't do any form of regularization, so that might be here our friend KNN, that this performs pretty badly. Same is also true for the nearest shrunken centroids. And then there are techniques which use L2 regularization. So they regularize against overfitting in this task, and this can work quite well. But yeah, like I said, the model is still, uses all of the features. But there's also stuff like this here. So well, I guess that's in both cases. Well, yeah, we have the lasso on the lasso regression with one versus all. We have the L1 penalized multinomial, or the lasso here in the elastic net. And they not only work quite well in terms of test error, but they also give rise to a pretty low dimensional model, which might be much more interpretable, and we now might go back, I don't know, to the guys from medicine or from bioinformatics and talk with them about these selected feature sets here, and they might be interested in now running some subsequent tests and so on to study the matter further. That's usually what they're interested in. They kind of want to have a list of ranked genes for further exploration. Third example, again, in a certain sense on microarray data. So here I want to study integrated feature selection a little bit, and maybe this would be enough. Maybe this would already work quite well. So why do we then have to learn some extra techniques? So this here is now simulated microarray data. So I took that from specific R package where feature selection techniques on such microarray data are provided and studied. And here we now generate a data set with n equals 200. We create now 100 features. So feature dimensional here, I guess, of medium size. We again use a multivariate Gaussian to generate our feature data. And the features are constructed in such a way that 50% of them are actually relevant for our target. They provide some useful information, and 50% have no influence. So 50 features are useful, and the other 50 features are not useful at all. I'd kind of like to filter them out completely. And then for the 50 interesting and useful features, they have kind of different amount of relevance for the target, different amount of information they carry. So there are some features in there which you can identify pretty easily, and some are a bit harder to detect because they have a lower amount of information they provide in identifying the target. So among those 50 relevant features, there are 25 which are positively correlated with the target and 25 are negatively correlated. And if we go down this list from the first one to the 25th, this correlation becomes smaller and weaker and weaker and weaker. Target is simulated from Bernoulli distribution, so because it's binary classification. And if we look at the decision boundary, I can't show this very well here in a 100 or 50 dimensional space, but if we look at something like a 2-dimensional slice through the data, you can see that the whole thing is like simulated in, well, I guess that's a direct result by us using multivariate Gaussians, in this case with pretty sure similar covariance structure, or equal covariance structure. So it's simulated and generated in a way that the optimal decision boundary would actually be linear, which becomes relevant now on the next slide, which is also the final one for this session here today. So we now compare several classifiers regarding their misclassification rate. And 2 of these classifiers actually have integrated feature selection. So that would be the R part and the random forest. So maybe let's go through the techniques here, and the classification algorithms. So first one is R part. So that's just like the implementation name for the CART algorithm. So for the decision tree in R, so R part for recursive partitioning. That is exactly the CART algorithm as published by Breimann. There's LDA for linear discriminant analysis. There's logistic regression. So both of these I'm running in the unregularized version. There's the naive Bayes algorithm. There's KNN with the 7, and the 7 just means K equals 7. So we're using 7 neighbors. And then there's the random forest. Now, why am I saying that the decision tree and the random forest have integrated feature selection? Well, first of all, I guess we can take a look at LDA, logistic regression, naive Bayes, and KNN, and hope we can agree that they don't do anything special in terms of integrated feature selection. Not anything special. They basically don't do anything at all for selecting features. But for decision tree, well, I hope it's obvious, right? So, if we create the tree here, some features in the tree will be selected and others not. And we, like in this greedy forward construction of the tree, we will always try to pick the feature for the next split which is most useful for reducing loss, reducing risk, reducing error. And if I have a 100-dimensional feature set and then my tree only uses 5 of these and then it's finished, well, I guess these 5 features have been selected by our decision tree algorithm. And because the random forest is actually an ensemble of trees, it also has some integrated feature selection. So I guess we have to be a little bit careful here. So for the random forest, very often, I mean, the trees we kind of early stop, we might even prune. For random forest, we very often expand these trees pretty deeply. Can still happen that not all features are used, but usually the tree models are sparser. We also decorrelate things in the random forest, right? We only stochastically allow for certain subsets. So we do this column subsampling, right? And that usually results in the ensemble actually using way more features than a simple decision tree. But like I said, if some features are completely useful and without any information, and we can detect that pretty directly, they might also not be selected in the random forest. Now, why do I have 2 lines here in the result table? So the first line is just applying the algorithm to the data as is. And the algorithm has to figure out itself, I guess, that there are 50 completely useless features in the data set. And the second line, in a certain sense, is, I don't want to say cheating, but I'm kind of now using an oracle and just feeding the 50 relevant features to the algorithm and removing the irrelevant ones. Now, what can we see from that, from the result table? I mean, first of all, we can see that, and that's in a certain sense it's quite different to the results we've seen before and the previous example, that the models here with integrated feature selection apparently do not work perfectly well here, right? So if we look at our part, that has a prediction error of 44%, and for the random forest, and that's not even improved by us using the oracle for the relevant features, and for the random forest that has a prediction error of 36%. That is actually a bit improved that's quite considerably improved by picking the relevant features. What we can also see is that for basically all other methods, it apparently helps a lot to just use the features which are relevant. So if you would have some oracle feature selector, that's likely going to improve predictive performance. What we can also see is which of these model types seem to work better. I guess we could maybe now talk about what's the best model anyway for that data set. Seems to be either this guy or this guy. Now LDA and logistic regression both fit hyperplanes to data, and they are also, I mean, they're different models and constructed by different principles, but usually the decision boundaries of these 2 models do not look totally different for many applications. And why does this work so well here? Well, like I said, data simulated in a way that linear decision boundary is optimal, and this is exactly what these 2 types of methods learn. This is also why the forest and the tree do not work so well. I mean, especially the single card tree, the single decision tree, because that only performs axis parallel splits, right? And that's pretty hard then to approximate such a linear decision boundary, which is not parallel to the axes. And the random forest, of course, can do a better job here because it combines hundreds of these trees, but they are still made up from these axis parallel, steppy functions. And it's quite interesting that even though the random forest is potentially able to learn this, and it also has this integrated feature selection, can still improve that, right? By putting some extra feature selection on top of that. Best would actually be here this LDA or logistic regression model. And of course, I guess we could have achieved a very, very similar effect by using an L1 or an L2 on top of the model. So that concludes the session for here. In the upcoming sessions, we'll now look at filters first and then wrapper techniques.